All right, thanks, Moises. Um, let's. This will be a quicker adventure than it was in February when we looked at the box culverts. We don't have refinements, although they could be applied here a bit, I guess. But this should be a much more straightforward document to get through. And so we're talking about pipes, circular pipes, and arch pipes. And the first thing you notice on the front is that our cover to our document doesn't look anything like it did for the box culvert guide back in February, and that's because when Moises submitted the one back in February, he was told it was inaccessible, and so we ended up using the new template MnDOT has. So it's to make it a little more accessible in the PDF front is why it looks different. Overall, what I hope to do today here is go over a few introductory items. We'll go over the guidance document itself. It's relatively short. We'll step through the Excel spreadsheet rating tool, give you an idea of what's in there and how things are organized. Ursula's done a lot of work on that. And we'll step through a quick little load rating problem here. So let's keep going. So within the world of MnDOT, concrete pipe structures are typically presented in standard plates. Since 1940, round pipes have been presented in the 3000 series, and I think currently it's 3000M is the edition of the 3000 series standard plate for round pipes out there. And pipe arches have been in the system as a standard plate since 1958. So if you have structures that are arch structures older than 1958, they probably are not standard plate structures. And the same for circular pipes older than 1940. We'll step through our guidance document and the load rating spreadsheet, and your other resources, of course, are Dave and Moises. So at the end of the day, the preference is for as many of these structures as possible to be load rated with the spreadsheet. For you to complete Form RCCL with the data that comes out of it, and that you would do a printout of the input and output, put that into a PDF file, and send both the RCCL file and the input-output PDF file to State Aid and Moises. If you've got a pipe that doesn't fit D-load criteria, which is 1960 and earlier, you may need to do a physical inspection rating because there was not a D-load specified for those structures. And we'll talk about D-load in a bit here. So how did we get to the pipe culvert world here? And so about a year ago, Moises had the roster of culverts assembled, and he sent it over, and Ursula did some pivot table work, and a couple of years ago, people did the work on the CMP metal culverts, sort of in the third column here. The box culverts took out, over half of the structure inventory there. So the precast boxes and the concretes, the C's and the W culverts are up in these two boxes. And what we're talking about today are the precast pipe arches, which covers 3,100 structures. So it's a good part of the inventory, and precast pipes are a much smaller part of the bridge inventory. I think there's a lot of pipes out there. They just may not constitute a bridge structure. When we look at the precast pipes, there are the arches and the culverts, and then there are the number of spans, or in this case, the number of pipe barrels that are associated with the different types. And so most of them are 2 or more barrels in these structures. So when you're out in the field, you aren't going to necessarily see big structures. So this first column here implies that the pipe is 10 feet or more in size. And so there's quite a few of them, but there's a lot of them that are multi-pipe structures. So one of the things Ursula and I had to do was to learn how to talk pipes, and we don't talk pipe naturally, we talk bridges naturally, I guess. So we had to learn a little bit about what a pipe class is in the world of conventional civil engineering, class 1 through class 5 pipes. We had to learn a little bit about installation types, type 1, type 2, type 3, and type 4, and we'll talk about that a little bit. We learned about two types of D loads. We learned about projection ratios, which is a ratio of how much bedding is compacted near the pipe during installation. And we learned about bedding factors a little bit, which are part of the equations we need to use. To learn how to talk pipe, we found it helpful to look at the American Concrete Pipe Association's design manual. It's a free download. The front part talks about hydraulics and things we didn't care so much about, but there are descriptions of beddings and different definitions of pipes in there, and so it's a good resource to have for a free download. So when we start looking at round pipes, as I mentioned, the very first ones arrived in standard plate format from MnDOT in 1940. This is the 1947 version of the original 1940 plate. It's 1 or 2 layers of reinforcement and round with sort of a beveled joint to transfer shear across the interface from one pipe to the other. 4 foot, 6 foot, and 8 foot laying lengths were typical, but these original ones from 1940 did not have D loads, and D loads will be important later on here. We fast forward to the current round pipe characteristics. Mr. Sterbicki signed a relatively fresh set of standard plates in 2020. We have the old-fashioned male-female joint, but we also have an optional bell joint that can be used on these round pipes as well. And so they still have 1 or 2 layers of reinforcement. There are 2 different wall thicknesses that the pipe's produced in, a B class and a C class wall, and you can find those in the standard plates. And what's also here that's most important are the ultimate load D loads. And so we'll talk about what this D load test looks like, but there's 2 levels that the current pipes need to satisfy. The first one is a pseudo service load, and that's the amount of load put on the pipe to get 100th inch crack formation in it. And then the one we're going to be really focused on is the ultimate load one here, where for class 2 pipe, it's 1,500 pounds per foot, and it ramps up to class 5 pipe where we have 3,750 pounds per foot. And so those are units that I wasn't used to beforehand, and so we'll talk about those a little bit later on as well. And so fairly conventional concrete strengths ranging from 4 KSI to 6 KSI. If we do sort of a parallel look at what's happened with pipe arches, the first ones showed up as standard plates in 1958. Smallest ones were 18 inches at that point in time, and the biggest ones were 84 inches. Again, they had 1 or 2 layers of reinforcement. And the very first set of standard plates did not have D loads included. And they showed up pretty shortly after, so you won't find a lot of them that don't have D load criteria with it, but there are some. So similar to the round pipes, the pipe arches have a relatively fresh standard plate from Mr. Sterbicki in 2020. They range in size from 22 or 18 all the way up to 132 or 169 inch spans. They have slightly different class labels for the D load test, but again, there's a 0.01 inch cracking load, and then there's an ultimate load. And so they range from 2A at 1,500 pounds per foot, to Class 4A at 3,000 pounds per foot per foot. So this deload that we're talking about is a 3-edge bearing test. And basically, the pipe is supported on 2 steel bearing strips of some sort on the bottom, and it is loaded through a single point on top. And excuse me, I apologize for that. It's loaded until it either cracks and produces the 1/100th inch cracks, or it fails at ultimate load capacity. And so this is what that 3-point load test looks like. And it's got non-typical units. And so if your diameter in here is 12 inches, 1,500 pounds per foot will be 1,500 pounds per foot. If you've got a 2-foot pipe, you would have 3,000 pounds per foot. And so this last foot unit is corresponding to the diameter of the pipe itself. We'll talk a little bit about projection ratios, and the spreadsheet does not use them for round pipes, but I figured I wanted to just give you an illustration of what the projection ratios are. So you have a dimension that is the vertical out-to-out height of the pipe, and the projection ratio is the part that is above the compacted fill supporting the pipe. And so up to the spring line, you can have a ratio of 50% of the pipe exposed or not in compacted fill. And so these ratios vary. And so in the spreadsheet, you'll see a projection ratio for the arch pipe, and it's a similar feature here. You have got a vertical height of BC prime, and the part that's above the compacted fill is the row, or the ratio of that's exposed, that's in the embankment around the pipe. So I was unfamiliar with what installation types are in pipes, and basically what they go from is basically very little care used for installation for type 4. It's basically dump material behind the pipe and no compaction is required. So as a result, the pipe doesn't receive extra load capacity from the surrounding medium. And so these go from poorest bedding condition to the very best. And so you can see that you get to 90 to 100% compactions on the lower side, 95% in the haunch, and then it drops as you go down to the different types of installation. And Dave and Moises met with Andrea Hendrickson and others in the hydraulics group. And if you do not know what type of installation you have based on plan documentation or specifications, you should assume a type 3 installation is what you should assume as a default MnDOT installation. So when we get to analyzing our pipe for load rating analysis, we've got a couple different approaches. We can do things similar to what was done in BRR for box culverts, where the structure is broken up into a 2D structure. We could have 8 or 16 points around the circumference. And let me turn my mic off while I cough here. And so we could break things into a structural model and put reinforcement in it and wall thicknesses and add loads and just basically replicate what's done in BRR for boxes for a pipe. And that's what we would call a direct analysis approach. Otherwise, an indirect approach, which seems much simpler for these pipes, is to use the deload or the indirect design method to evaluate these for load rating. So if we're looking at our BRR box culverts, we've got our self-weight dead load, we've got dead load of a wearing course, we've got vertical earth, we've got horizontal earth, we've got earth surcharge, we've got live load surcharge, and we've got live load plus dynamic load allowance. And we need to worry about that for shear and thrust and bending moment at all the locations in our cross section. So it gets to be a lot of data to handle. For the indirect pipe analysis approach, it's really pretty simple. All you need is the span of the pipe on the inside, this D ultimate capacity in pounds per foot. This 12 here converts the span into feet, so you end up with a pounds per foot capacity. So we need to have the rest of our terms in these equations be pounds per foot as well. So we've got a load factor for earth loads. We've got a unit or a weight per foot for earth loads for our pipe. We've got a load factor for fluids, water in this case, and we've got a weight per foot for the fluids. And then this bottom term is a bit new. It's a bedding factor for earth loads and the fluid loads. So this is a bedding factor. We've got a load factor for our live load, and then we need to turn our live load into a pound per foot live load. And then we've got another bedding factor for live loads here on the bottom. And so all we really need to do is bring this together in a load environment and not bring it through the section properties and analyze it locally like we would in a direct process. This indirect approach is described in some documents. One of them is a Design Data 1 document put together by the American Concrete Pipe Association, and this 10-page document is included in the spreadsheet as one of the reference tabs. On another reference tab is a white paper put together by Josh Beakley, the Vice President of Engineering for the American Concrete Pipe Association, and he basically steps through the indirect approach to load rating the pipes. And so that also is included in the spreadsheet tool. Looking at the guidance document itself, we've got a short introduction on the background for the concrete pipe and pipe arch standards. We've got some tables talking about characteristics of those. We've got a little description on classes of pipe and pipe arch. Then we've got an overview of the rating procedure, and then the spreadsheet workbook tabs. We've got a description for each tab, the information contained in that tab and what it's intended to do. And then on page 25, we have a short example we step through. And then the rest of the guidance document is really the standard plates, starting from 1940 for the concrete pipes, and then 1958 for the pipe arches. Looking at the rating equation, again, we really can get this first term very quickly. It's simply the size of our pipe from at the spring line in the horizontal direction in inches. And the D ultimate, we can pull readily from the class of pipe that we have used or installed at the site. So whether it's class 1 or class 5 or something in between, we have ultimate D load in pounds per foot that we can use. If we look at the second term in the numerator on the rating equation, we've got a load factor for earth load, a load factor for fluid load in the pipe, and then we've got these pound per foot loads for earth load in the pipe carried on the pipe, and then we've got a fluid load in the pipe in pounds per foot, and then we've got a bedding factor. So those are relatively straightforward to get to. And the real work is in the bottom because we've got a lot of vehicles to get through. So gamma LL is the live load factor for the different live loads we're considering. WL is the live load carried by the pipe in pounds per foot, and BF is the bedding factor, which this is a typo. That should be BFLL here to replicate that, so I apologize. So inside the spreadsheet, you will see a couple introductory tabs to the left, but when you get to tab 1, you've got some input data on the size of pipe and cover, things of that nature. Tab 2 has live load, multi-presence factors and load factors that need to be confirmed in this area. But other than that, the tabs are relatively well aligned with what's going on in the spreadsheet here. So D Ultimate is on tab 9. You can find what's going on there. You really don't need to do anything, but that gives you information on where the D loads are coming from. WE and WF calculations are on tab 6, and so you can find that part of the equation here on tab 6. Bedding factor for earth loads is on 7. Bedding factor for live load is on tab 8. The reference documents I talked about, the design data 1 is on tab 10. The white paper is on 11. And off to the end here is tab 12, where the permit vehicles and load factors for legal trucks are computed out here. And so we'll talk about that a little bit later. So let me bring up the spreadsheet here and see if I can make this big enough to be a little easier for people to read. And so the very first tab is an introduction, and it talks about what the specs the spreadsheet complies with, that we looked at the MBE 3rd edition with the 2020 and MnDOT's load rating manual and things of that nature, and a short description of the different tabs in the spreadsheet. So that's the introduction. Tab 0 is the guidance piece. So when MnDOT has additional guidance to provide concerning the rating of pipes, it'll go on this tab. So this talks about the assumption for both round pipe and pipe arches should be a type 3 installation unless you have extra information. So guidance elements are on tab 0. Tab 1 over on the left looks a lot like the CMP spreadsheet, and then as you move to the right, there is information to help you populate the green cells. So in general, you would put information in the green shaded cells. Output would be in the gray cells, and so some of these are free form, like the year of construction or the year built. Others have drop-down menus, so you can choose an arch pipe or a circular pipe. And so there are some fields that apply only to pipe arches and some that apply only to circular pipes. And so it'll take a little bit of time to get through that, but it shouldn't be too big a struggle. Input the size of the pipe here, whether you've got B-wall or C-wall for round pipes. You would put your height of fill over the top of the pipe in this cell. And one thing that is different from the corrugated metal pipe is that instead of only granular fill, the ACPA approach allows a person to evaluate a non-granular fill over the top of the pipe as well. And for MnDOT, I think almost all our structures will have granular fill over the top, but there is an option to use a different soil, and that's assumed to have a lesser spread of load through the overburden, so it concentrates the loads a bit more. There is a field here to populate for which direction traffic travels relative to the orientation of the pipe, whether it's parallel or perpendicular, and I'm guessing most cases will be perpendicular. Then there are a number of fields that get filled in automatically. And then if you had arch pipe, you would populate this with the square feet that the pipe has for water area, so the dead load from the water weight can be computed. This is where you would insert the class of pipe you're looking at. Depending on the bid documents and pay items, you should be able to identify what class the pipe is in many cases. In almost all cases, you're going to want the D load to be the D load type you look at, not the cracking load, but both sets of data are included in the spreadsheet if there is an odd case where you would want to look at that reduced load. The system factor in almost all cases should be a 1, but if there's a need to scale the load that's applied to the pipe, you can apply that here in the system factor. And the condition factor is where we would add the fee factor for whether we're in good or satisfactory condition or fair condition. So we're assuming this is a 0.95 for this particular input, so we're assuming it's a superstructure condition code 5. And then down below, the rating factors pop out, but you can't run there right away. You need to do a couple things before you jump on those and think you're done with your work. Similar to the metal pipe spreadsheet, there are columns for each of the vehicles that are being evaluated to compute the footprint of the axles, one wheel, one axle, multiple axles that are combining depending on the depth of the fill to compute the pressures that the pipe is carrying. And so we've got M3s over here on the left, and we have the C single permit vehicles over on the right. And so there's not much to do on tab 2 other than the green cells down here. So if you have multiple presence factors that you need to tweak, that can happen here. And the ACPA procedure assumes 1.0 for multiple presence. They're assuming traffic meeting over their pipe with a 4-foot distance between the wheels. You can adjust your live load factors for your permit and legal loads here based on ADT, and that's what needs to happen here on tab 2. And the rest of it, these gray tabs are primarily just background information, so you can see what's being used to come up with the computations. And so this sheet has how to compute the soil prism loads for vehicles traveling perpendicular to the pipe. And then there's another one. So the top is the granular fill with that 1.15 spread. The other soil is assumed to have a steeper slope or a 1.0 H for the live load distribution. And so those pressures are a bit different. So there's 2 tables here for perpendicular to the pipe. There's a couple tables here for vehicles traveling parallel to the pipe. And so if you're interested, you can hunt in there to see how things are computed. Tab 4 is basically a spot where you can see that our 1995 30-inch round pipe had a 3.5-inch wall thickness. So basically Ursula's taken the standard plates for both round pipe and pipe arches over the years and put the data in tables that will sort of flow to the front part of the spreadsheet to get the geometric parameters we're looking for. So there's both the PDF version, the image of it, plus data in tables. But ideally, you can just refer to this and confirm the numbers look right. You shouldn't need to do any computations back here. And if for some reason you need to change the footprint of your wheels, so this assumes we've got the 20-inch wide, 10-inch tall or forward direction footprint for our contact for our tire. If you need to change that, that can happen here on this. And then this also gives you the slopes for the other soil and the granular fill. That could be tweaked there if you had a need to do that. She's also taken what you input for a type of installation and computed bedding factors. And so the uniform earth load for this particular case is 1,036 pounds per foot, as she's worked through the fill height over the top, the size of the pipe, and then this vertical arching factor or soil structure interaction piece. And then the fluid weight of 306 pounds per foot is automatically computed here as well for circular pipe. So we keep moving. We've got a bedding factor for earth and fluid pressures. And so as you get a better installation with a smaller pipe, you get the best distribution of load. And so as you get to cruddier installation, you get a penalty that your load doesn't get reduced as much. And so Ursula's got it set up so it interpolates to get your correct bedding factor based on your size. And then the projection ratios will get used down here to compute the bedding factor for pipe arches. Again, it's here with reference material for you to look at should you want to look behind or look under the hood a bit more. Similar process here for the bedding factor for live load. The deload tab simply has a roster of the deloads for the different pipes to be used. Tab 10 has the 10-page design data sheet that really talks about how the loads are assembled in our spreadsheet. It's based on the formulas in here, which are very similar to what AASHTO has for load distribution. And so later on, you'll see things about figure 3, figure 4, figure 5. That's just whether or not our wheel loads are overlapping with each other or axles are overlapping to get the spread A and spread B dimensions. So if you want to look, there's a lot of information here on tab 10. Tab 11 has the white paper, talking about, load rating the pipes as we're doing in the spreadsheet here. And tab 12 is at the end, and this is the one that you will need to look at and bring forward load factors to be placed on tab 2. And so some of these load factors are dependent on ADTT. And so what's intended to happen here is that you would, carry your ADTT here and then bring in the correct load factor. If it was 1,000, it'd be 1.3, etc. Over here, different vehicles have different gross vehicle weights per AL. And so we have different load factors for those. And so with 1,000 ADT, these have a 1.25 load factor. These have a 1.35. And so keep going over to the right. You get your single permits. And last but not least, we've got a 1.3 load factor for the emergency vehicles off to the right. So the idea is you input your data on tab 1. You come to tab 12 here, you get your load factors figured out, and then you go back to tab 2 down here and input the appropriate load factors for your ADTT and whether you've got mixed traffic or traffic all by yourself. Those load factors get populated here. After these are populated and confirmed, you can go here and then you can read your load factors out to put on your RCCL form and make Moises happy. So it's tab 1, tab 12, tab 2, and then back to tab 1 is the process here. So that's the spreadsheet. And so the real trick is really getting that soil load onto the pipe and figuring out what that load per foot is. And it's dependent on which direction, because that's not quite a square, so there is the direction of travel. I know you're going to find pipes that aren't perfectly perpendicular or perfectly parallel to travel, and so if your skew angle's under 45 degrees, assume it's perpendicular. If it's over 45 degrees, assume it's parallel. And so the real work in getting this rating done is getting this live load figured out for the depth of fill over the pipe. And so basically Ursula took the CMP loading tool or loading sheet and worked it with all these vehicles to get the rating factors. And so I think we already talked about that. And we talked about those 4 tables, 2 for perpendicular and 2 for, and we talked about the rating factor at the end of tab 1. And so I'm just re-echoing here. Enter your data in the green cells on tab 1, which is your general input. Enter your data on tab 12 in the green cells to get the appropriate live load factors for your conditions in ADTT. Transfer these load factors to tab 2, and then review your output on tab 1. And so with that, I want to just scroll real quickly through the guidance document itself and show you what's in there. And so the cover, we talked about it being different. We went through the table of contents. We've got a little introduction. Then we've got a couple tables here. So the purpose of these tables is to let you know that what's inside a standard plate detail. So if you've got something older than 1940 that's round, you know there's no standard plate for it. And if it's older than 1958, you're not going to have a D-load with it. And so this gives you the sizes of pipe that are in those standard details and the date they were approved, just so you can figure out if you need to do a PIR or some other method to get to your solution, because our spreadsheet is working with the D-load pipes. And so that's the roster of 3000 series standard plates. Here's the Strabicki one, 12-inch to 108-inch round pipe, and there's 6 sheets to define it. Same thing for the pipe arches, 3014 series, 1958, 18-inch to 84. The first ones did not have D-load, but by 1961 we did. So if your year constructed is after 1961, you should be in pretty good shape. Classes of pipe, we have a little description about the 2 different D-loads and the classes that are presented on the standard plates. Similar discussion about pipe arches. And there are notes in some of these standard plans that if you have no idea what class pipe may be installed, you could possibly work backwards from the general notes. For this particular case, the class 2A was supposed to be used for depths of cover up to 8 feet, class 3A for 16 feet, and class 4A for 23 feet of cover over the pipe arch. Talk about the rating procedure. talk about the components that are used for bedding factors, and then we give a little description about each of those work tabs, similar to what I just stepped through with you guys. So from tab introduction through tab 12, we've got some descriptions in here. And we talk a little bit about putting input data into the different fields as well. And so year built, pipe shape, pipe installation type, projection ratios. So we give you a little figure to help you understand what those mean. So one of the things we didn't have populated when I went through was this arch concrete pipe input water area. And so if you've got a pipe arch, you've got sort of a nominal span, and then you've got equivalent diameter. This input water area is the water area in the standard for the different size pipe that you'll find. So that comes off the standard. We've got those descriptions we talked about, and the rating factors come out. We talk about what's going on tab 2, that you need to bring your data forward to row 56 and 58 for multi-presence factor and live load. And then what's happening on the other tabs. And then at the end, we've just got the pile of standard plates. And so I think we've got one example in here. I'll get to that here real quick. So we talked about the design data reference material in there. We talked about the white paper. And then tab 12, populating the green cells with the ADTT to get, and then putting the load factor in there. So to illustrate use of the spreadsheet, we took the example from the concrete pipe design manual with less, and so this is their example, 30-inch diameter pipe with B-wall installed as a storm drain, subject to AASHTO loading. It gives information about trench loading, but we're not going to take advantage of the benefit of a trench. We're just going to assume embankment and use AASHTO criteria with select granular soil, and here's that type 3 installation. The other information we need is the class of pipe, and so for this example, we'll assume class 2. We'll assume it was constructed in 1995. We'll assume the inspector gave it a condition code 7, and that our ADTT is 1,000 trucks per day. So, and we'll assume that special permits are single trip and that other traffic may be on the bridge with the permit vehicle, and that should give us all the information we need to populate the spreadsheet. So we go in here, we give it a name, a description, a bridge number, year built, and go in the drop down, hit circular pipe. Go in the drop down, hit type 3 installation. It's not an arch pipe, so we don't need to worry about that projection ratio. It's 30-inch diameter pipe. It's a B-wall, and we got 2 feet of fill over the top, granular fill, and the traffic is perpendicular based on the figure. We don't have to worry about the water area because it's a circular pipe. We'll select a class 2 pipe. We're selecting D-load for the capacity of the pipe, if you will. The NBI 7 gets us to the 0.95, and then we've got a system factor of 1. We head off to tab 12 with our ADTT of 1,000. It's right on the threshold, so we'll use load factor 1.3 for those vehicles, and the same over here for specialized hauling vehicles. Permits, we'll look at our vehicle weights and see which category we fit in here, and so we're in the 2 to 3 range, and so these are 1.25 load factors. Down here we're below 2, so that's a 1.35 load factor. And then we do the same thing with the special single permit. We carry those load factors forward to row 58 on tab 2. And here's screenshots of what I populated there. Once I confirm those are correct, I can go back to tab 1, and then there's the rating factors for each of the vehicles. And that's what's involved. And after that, we've got the standard plates or round pipes, and then that's followed by the standards for arch pipe. And so I won't go through all of those. And so I think that is what I have